Hi, this is the second part of our lecture 4. I'd like to start with this slide from the first part. It seems a little bit strange that we have this nice constant feed for both test and train and scale, so just the same accuracy for different number of neighbors. And the reason is that I redefined our training data somewhere below and then started this cell. So this is the right, just a moment. Yeah, this is the right graph. So I accurately recreated this experiment. So just to remind you that we wanted to compare two versions of k-nearest neighbors classifier. The first one was just an ordinary k-nearest neighbors without any additional preprocessing, without any transformers. And our motivation to modify it was the fact that in our dataset we have features with different range. So, for example, we have features like the number of class from 1 to 3. Also, we have features like fare ticket price, which varies from several dozens to several hundreds. And within k-nearest neighbors, we calculate distance, Euclidean distance between points, and these features with large range contribute the 90% of this Euclidean distance. But these features can be unrelated to our target variable. So one way to balance this problem and to take into account kind of a more fair distance metric is to normalize our data, is to scale all the features to have zero mean and unit variance. And we can do it if we use pipeline and add one more step before our k-nearest neighbors to scale the features. Standard scaler just does the job. And also we have some Python magic here. So the first one is list comprehension. I just iterate within using this nearest neighbors range, so to vary the number of neighbors, and use this function to calculate train and test errors. And then, so at the end, I have a list of say 100 or 99 pairs, and then this construction zip plus this asterisk allows me to convert this into two tuples of 99 errors. So then I just visualize it, and the result is here. So I'd like to notice that here I also converted the x-axis. So you see it started from 100 and ends at 0 to be consistent with this graph. So we have low complexity on the left and large complexity on the right. Also, I tried to preserve colors. So red curve here, the red one, can be interpreted as our train error, and the black one can be interpreted as the test error. So here we have these curves for two scenarios, with standard scaling and without. So as we can see, for unscaled data with just k and n, we have less accurate models both on train and test sets. So the difference here is approximately from 10 to, it's likely 10%. So this really simple addition to our pipeline allows us to increase the quality, maybe not as dramatically as it was in that example from the previous part, but still it's a really consistent improvement. As you can see, we have this delta, this additional accuracy for all for almost all values of complexity of our model. Okay, then I'd like to switch to the main part of this main topic of this second part, and I want to discuss metrics, how to measure quality of your binary classification models. So for binary classification, we have 4 different options. So just to remind you that we have just 2 classes, say survived or not survived. And usually we name it as negative and positive. And usually negative means that there is no event, and positive that there is an event. And then in our cases, positive is survived. And then for any classifier, we have 2 types of answers, negative and positive. And then in total, we have 4 possible combinations. The first one is that the true answer is positive, and our classifier predicts that this point is positive as well. And this set of points is called true positives. Similar, if the true class is negative and our prediction is negative, these points are named true negatives. Then we have 2 types of errors. The first one is that actually the answer is positive, so this passenger survived, but our model predict that it didn't survive. So this is false negatives. We said negative, but this is not correct. And finally, we also have another type of error, and the true answer is negative, but we predict positive. And it can be visualized in this way. Actually, it's kind of a non-trivial image. For someone, it really helps to understand these 4 classes, but for others, it just doesn't work. But we can try to use it. So this green part, the left part of these graphs, are positive elements. I mean that the ground truth label, the true answer is positive. And this part, the right part, are negative points with answer equal to 0. And then this circle is the set of our answers. So the points inside this circle are predicted as positive points, and outside this circle are predicted as negative points. And we can introduce several metrics actually, but the most important metrics are these 2, precision and recall. So precision, it's the ratio of true positives to the overall positive predictions. So precision allows us to estimate how many predicted points are relevant. And so imagine that we want to predict a serious disease or a failure in an airplane. And we want to identify these failures before the actual event to replace some details in the aircraft. And so for true positives and true negatives, well, it's fine. It's more or less clear that we did a good job. But the price for false positives and false negatives are different. So if we predicted a false positive, it means that we say, aha, there will be an error, and then the price is that we need to pay to a technician, we need to check this detail, for example, or we need to pay for the replacement. This is one price. A different price is paid for false negatives. So false negatives, we said, oh, it will be fine. So this aircraft is okay. But then an event happens and we need to pay more because our aircraft cannot return to our base airport, and we need to send technicians, we need to send details to another airport, we need to refund money to passengers, etc., etc., etc. And precision and recall allows us to estimate the balance between these two scenarios. And in this particular case, in this particular example with aircraft failures, it seems that we really want to minimize the number of false negatives. So we want to maximize recall because the price for false negatives is too high. And in this case, we want to maximize recall, and precision is connected with recall. And usually, if we increase our recall, we decrease precision at the same time. It's not a monotonical dependence, but usually it's connected. And we will see a little bit later that we cannot boost both metrics. Okay, great. And then you can use, and there is another metric, F1 score. So as I said, precision and recall are just different in terms of, so we need to select, do we want to increase recall or do we want to increase precision? And it's hard to compare two different classifiers, one with good recall and bad precision, and the second one with good precision and bad recall. But we want to compare these two classifiers somehow. And in this case, we can use F1 score. This is just a way to average both precision and recall to get just one number instead of two. So for us, it's just more convenient to use just one number, and it's easier to say that this model is better than this one. And also we can use this classification report function from sklearn metrics to generate a report like this. So we can calculate precision and recall for actually all classes. Now we have just two classes, survived and not survived. And we can say that the positive label is 0 and calculate precision and recall for this positive label against all the others. But right now we have only one option. But imagine that we work with a multi-class problem. In this case, we will have more rows here, say 0, 1, 2, 3, if we have 4 classes. And then in each row we have precision and recall if we consider this label as positive and all the other labels as negatives. And also we can calculate some average values for using slightly different approaches, but as you can see, there is no difference or almost no difference. So we can just think that we can calculate precision and recall separately and then just average somehow. So this is the way to calculate all the metrics simultaneously from your predictions. Also, for some reasons I added this part of code. It seems that there were some warnings in logistic regression, and I just wanted to remove these warnings from my Jupyter notebook. And convergence warning, it just says that the optimization problem behind particular model, in this case logistic regression, it didn't have enough iterations to converge. And sometimes it can be crucial, but usually even not fully converged model is quite good. So here also we have two additional functions, cross-val predict and logistic regression CV. I referred to the seminar, so I sorry that I didn't remove these parts, but it just this is a function to just do cross-validation, and this is a little bit trickier, and this version of logistic regression allows you to automatically select the best complexity. So internally it split your training data into several parts, then perform cross-validation for different sets of complexity parameter, and then select the best complexity parameter based on these cross-validation results. So it just the replacement of several lines of code. You can do it manually, as we did, for example, for k-nearest neighbors. We iterate through different values of k of n neighbors. This is the measure of complexity for k and n, and then we can just select the best, the optimal value. So this is exactly the same, but implemented inside scikit-learn. So you don't need to replicate this cycle and iterate over different cross-validation splits. Okay, so let me return to metrics. As I said, we can calculate a huge number of different ratios from these four numbers. So still we have true positive, true negative, false positive, and false negative. But we can calculate, as we can see, this is again from Wikipedia, we can calculate a lot of different metrics. Usually you need only 3 of these numbers. So in addition to accuracy, so accuracy is more or less simple. We need precision, recall, which also sometimes is called sensitivity, and specificity. So for computer science papers, usually people use precision and recall. For some applied problems like, for example, medicine or biology, people usually use sensitivity and specificity. So sensitivity and recall is just the same name, different names for the same ratio. Sensitivity and specificity are connected in that sense that specificity is actually recall for zeros. So you can calculate recall for zeros. For example, you can extract it from a classification report. As you may remember, we have recall for both zeros. So actually this number is specificity, and this number is sensitivity. But precision and recall are not symmetric, as we can see from these formulas. So these can be they are interchangeable if we replace the definition of positive and negative. So just use a different order of labels, but recall and precision are not interchangeable. So we can move further and discuss precision recall curves. So let me start with, again, a simplified image without these additional ratios. We just need these these ratios, and TP stands for true positive, FN false negative, false positive, and true negative. I guess it's clear. And now we can calculate these ratios for our Titanic dataset, and for to play with different options, we can use logistic regression instead of k-nearest neighbors as we did before. So we can start with just default model with default complexity and train it, and then we can plot this. We can calculate precision and recall, and we can plot it. So to calculate it, you need precision score and recall score functions from scikit-learn metrics, and then you just pass your ground truth labels, your predictions, and then plot this star point on the graph. It's more or less clear that we have almost 0.7 recall and approximately the same precision. But as I mentioned, in addition to the binary labels, so we can just check that our predictions, we can print it, say the first 5, and also let me remove this part. So you see, this is just binary numbers, 1 or 0. Also, we can print the sorry, let me check that we still work with logistic regression. Yeah, the point is there in the same position. Okay, and we can print these predictions, and in addition we can print these probabilities. So to calculate predictions, we use this method of our fitted classifier. Also, in addition, we have this additional method to predict probabilities, and we can compare the outputs. So I just printed the first 5 outputs of my classifier, and as we can see, probabilities are two-dimensional array, and we have probability of 0 class, the first number, and the probability of the second class, and this is probabilities, and in that sense that the sum is equal to 1. And we can see that for the first example we have larger probability for the negative class, and we have 0 here. For the second case we have larger probability for the second class, so the prediction, the binary prediction, is equal to 1, and etc. And obviously, to convert these predictions into these outputs, we just need to select a threshold and say that if the probability is larger than this threshold, then the predicted class is this or that. And usually it's just 0.5, as we can see from for example, this line. So we have approximately 50-50, but the first class still have slightly larger probability. So we predict 0 as our final binary prediction, binary label. But obviously we can move this threshold if we want to balance precision and recall. We can say, for example, if we want to cover more cases with positive outcome, so with class label equal to 1, we may shift our thresholds to smaller values. For example, we can say that we would like to say that if the probability of our positive class is more than 0.3, then our binary prediction will be 1. So in our case, this rule, this change threshold, will result in one change in binary output. So for the, not for the first, for the third case, this probability will be converted to these probabilities will be converted to the binary output 1 instead of 0. Or in opposite, if we want to increase our precision, so if we want to remove false positives from our predictions, we can say that we will predict positive outcome only if the probability is, say, higher than 0.7. And in this case, all these numbers except the last one will be equal to 0, right? Because we have a large probability only for the last case. So, in other words, we can create a set of classifiers using these probabilities. Not the only one, but really a set of classifiers. And here we can plot the precision and recall for the whole set. So we can vary this threshold. For each binary decision, we can calculate precision and recall, and then plot a curve instead of just one point as we did before. And this is a very nice curve because you can use this curve to select the right threshold. So, for example, if you want to work with high recall, you know that you need to select this point, and here you will have recall equal to 1 and precision will be equal to 0.4. So you will cover all the positive labels, but among your predictions, 60% will be false positives. Or if you want to maximize your precision, it may be reasonable from this plot to select, say, this point. So here you will have precision more or less equal to, say, 0.9, and recall will be 0.5. So you won't have many false alarms, and you still do cover approximately the half of the true cases. So it depends on the problem, of course, as we discussed. But this curve provides you a simple and intuitive way to select the right balance between these two types of errors for your particular problem. And also, we use here this average precision score. This is just the area under this curve, and it can be interpreted as kind of the average precision. And it can be also used to characterize kind of a single metric to characterize your classifier. Okay, the next type of curves are so-called ROC curves. Again, just to remind you, this simple table, and now we need to another two ratios. Actually, the first one is again a different name for recall. It's so-called true positive rate, and the second one is false positive rate. And as you can see, again, it's connected, but it's a different metric. And again, we can calculate just one number, but usually for these ROC curves, we calculate area under this curve. And the good thing about this ROC curve is that it's a good way to measure the invariant metric. I mean, in terms of, for example, the proportion of your labels of positive labels in your test sample. I mean that area under precision recall curve is not calibrated. It can be 0.2, it can be 0.6, so it's hard to compare different problems using this metric. But ROC curve has a very intuitive explanation. So the maximal possible value for the ROC AUC is 1. So just the ideal classifier, which is just this rectangle. The value equal to 0.5 says you that your accuracy is the same as for a random classifier. So it looks like R square. So 1 is the best possible choice, 0.5 ROC AUC is equal to a naive classifier. And the values less than 0.5 means that something is wrong with your model, because you can simply convert your predictions. So if your classifier predicts 0, you say 1 instead, and your ROC curve will be symmetrically converted to a value higher than with area under the curve higher than 0.5. So values less than 0.5 mean that there is a crucial mistake in your pipeline. So your predictions can be improved by just a random classifier. Okay, so this is a nice way to compare. ROC AUC curve provides you a nice way to compare your classifiers within different problems, because this nice calibration, nice physical meaning of these areas. Actually, yeah, this is an example, but we won't cover it.